Hello, my name is Ja. Today I'll be introducing my Illumination feature for Project Zero that I implemented as part of the extra credit. So let me show you an example of what it looks like. So here I've removed all the planets from the sample file except for Earth. You can see that here we've got a little orange outline around the Earth that follows where potentially the sun's rays would hit it. And so here we can see that at each moment, Earth being in perfect circular orbit around the sun, half the Earth is fully illuminated. Personally, this is a very rudimentary feature for a very rudimentary implementation of illumination. Seeing as it's not true ray tracing, the main advantage and why I chose to do it this way is this is very fast to compute. We only use basic trigonometry and the 4 basic operations, so it's very cheap to do, and it looks good enough, assuming if we can follow the assumptions we've made, which I will explain later. So at a high level, the algorithm, we simply compute the slope, the line through the origin using the position of the planet. That's just a rise over run. Then we compute the inverse slope in order to find the slope of the line tangential to the sun but centered at the planet at each position. We then use trigonometry, arctan, to find the necessary bounding angles to illuminate the Earth properly. And then I used standard draw libraries pen function to draw in increments of 0.08 units along the circle in order to draw the lighting correctly. A small adjustment I had to make was to handle the negative y quadrants, since due to how the arctan function works from negative pi to pi, it would actually reverse the lighting below. So I just had, so that was just like a simple sign change for so where all this code went, it went into the n body extreme class. I just added like an extra method to the for body in bodies loop, where we just compute the light for each of the planet, and then I modified the body extreme class to have a radius item, which was I found that a value of approximately 8 times 10 to the power of 10 works well for all the planets that we have right now. In the things that, so that now there are a few assumptions and future adjustments that I could make to this model. First is that currently this feature doesn't support multiple body illumination yet. For example, if we had like 2 planets here, both of them would be illuminated as if the other weren't there. That's a problem. It could be easily fixed due to how we draw the points by, if we just check for collinearity between each point. Say we check between this point, a planet here, and the center. If 3 points are collinear, we remove the one furthest. That could potentially be very expensive due to how we have to check it against every other point. There could be optimizations made, but I haven't implemented it yet due to lack of time. We could reduce the intensity at edges to better simulate real-world conditions. Currently, we follow the parallel ray of light assumption, where rays of light are hitting Earth at equal intensity around the world. This is not true, evidently, due to how the sun is positioned, but it's true at a local level, but not on a solar level. I'd also prefer to add realistic deviation and reflection of sunlight to act like true ray tracing. Unfortunately, without like a revamp of our entire methodology, this is unlikely to be possible. And true ray tracing can be very expensive, but this one, it's a good substitute. I had a lot of fun doing this. It actually took a lot of experimentation, and there are a couple of magic values in the code, but yeah, and I hope we do something like this again.